Hello. So today I want to discuss about a problem that appeared in INMO 2013. It's a number theory problem, mainly Diophantine equation solving. This is a nice example of factorial method to use to solve Diophantine equations. This will give you a general idea to how to solve this type of Diophantine equations. At the end of this video, I'll give you a similar type of Diophantine equation to solve. You can try that on your own. And after you have found the solution, like you have figured out one solution, you can type that in the comment box.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So let's begin. We have to find all natural numbers mn and primes p greater than or equal to 5 such that m times 4m square plus m plus 12 equal to 3 times p to the power n minus 1. So let's begin. Now let's try to factor it in a different way such that it becomes more comfortable for us to deal with. Because p power n minus 1 is not that useful, I try to make RHS something into p power n. Because for that we can use prime divisibility more better. So just expand these things out. We have 4m cube plus m square plus 12m plus 3 equal to 3 times p to the power. Now we can factor this thing out. Factoring this, you will just get that 4m plus 1 into m square plus 3, that is 3 times p to the power n. Now this equation is a lot easier to handle. Now see, let's define D to be GCD of these things, 4m plus 1 and m square plus 3. So we know that d square divides 3 times p to the power n. Now what can be the values of for solving Diophantine equations? GCD is really important. So let's check some cases. What if d equal to 1? So I have 4m. In these cases, I have 4m plus 1 and m square plus 3 have no common factors, and multiplying that I'll get 3 times a prime to the power n. And we also have GCD of 3 times p power n equal to 1. Why? Because p is a prime greater than or equal to 5. So p is not equal to 3. So GCD p comma 3 is 1, and so is GCD 3 comma p power n. So in these cases, what can be the all tuple values of 4m plus 1 comma m square plus 3? It can be 1 comma 3 p power n. It can be 3 p power n comma 1. This is the case where one of the number is 1. So for all the other cases, none of the number is 1. So all numbers are greater than or equal to 3. Now see, as they don't have any common factor, so both of them cannot have a factor p. So all powers of p are present in exactly one of them. Like any power of p cannot be present in both. Like in particular, any power of like p cannot be present in both. So all powers of p are present in exactly one of them. So we'll make cases. All powers of p are present in p power n. In that cases, 3 is either in 4m plus 1 or m square plus 3. If it is in 4m plus 1, we get the 3 p power n comma 1, and else we have p power n comma 3, and similarly 3 comma p power n is an option. These are all possible cases. Now, can we get any solution? Let's see. Observe that 4m plus 1, this is greater than or equal to 5, because m is greater than or equal to 1. M square plus 3 greater than or equal to 1 square plus 3, that is greater than or equal to 4. So in LHS, the minimum of these numbers is always greater than or equal to 4. But what is in RHS? In either of the tuples, the minimum is either 1 or 3. But in LHS, the tuple has minimum greater than or equal to 4, but in RHS it is 3 and it cannot occur simultaneously. So d equal to 1 have no solutions. So those tuples cannot be equal. So I have the GCD greater than or equal to 1 must hold. Now d is my GCD 4m plus 1, comma m square plus 3. Now as 4m plus 1 is odd, it is coprime to any power of 2. So I can multiply the number by coprime factor and that won't affect the GCD. So this is same as GCD of 4m plus 1, comma 2 to the power anything times m square plus 3 because I am multiplying by coprime factor. That won't affect my GCD. Now what can be my anything? See, I can try to use the Euclidean algorithm to compute the GCD to reduce it to a smaller case. In that case, one possible way is I can multiply by 4m in 4m plus 1 and subtract it from the other. So the quadratic part should be 16m squared. So in that case, if I take my anything to be 4, that will be 2 to the power 4 times m squared, that is 16 times m squared. So I can somehow cancel it out. This is an advantage. So I will take my anything to be 4. So this is just GCD of 4m plus 1, comma 2 to the power 4, that is 16m squared plus 16 into 3 plus 48. Now this looks interesting. Can you reduce it furthermore? This is same if we add them. So just add this thing. 16m squared plus 4m plus 49. Now this part, this is just 4m times 4m plus 1. I have got it. So I will just multiply this by 4m and then subtract it from the total equation. So just to get this is the same as GCD of 4m plus 1, comma 4m into 4m plus 1 plus 49 and subtract with 4m plus 1 and multiply it by 4m. This is the same because GCD of a comma b is same as GCD of a comma b minus any multiple of a. And I will take my multiple, here my a is 4m plus 1, I'll take my multiple to be 4m. So this is just GCD of 4m plus 1, comma 49 because the all other parts they are cancelling out. And 49 is just 7. And GCD are the divisors of it. So this belongs to either 1, 7 or 49. Now we know that 1 is not possible, so 7 and 49 are only possible options. So now let's make the cases. So D can be either 7 or 49. Let's see. Let's assume D equal to 7 and let's see in these cases what happens. Now what does D equal to 7 signify? We know that d square divides 3 times p to the power n. In either cases, like my GCD is a power of 7. So in that case, we must have p equal to 7 because if p is any other prime, we cannot have 7 divides that thing. And d cannot be 3 either. So p must be 7. This is a good observation. Now what are the all other possible things? We have 4m plus 1 into m square plus 1, sorry m square plus 3 equal to 3 times 7 to the power n. So what does that mean? My 4m plus 1 is of the form either it is a 3 into a power of 7 or it is just a power of 7. These are all possible cases. You also know that GCD of 4m plus 1 and m square plus 3 is just 7. So any bigger power of 7 cannot divide the both. So how can we use this thing? Because see, we know that 7 to the power k divides 4m plus 1. But we need to see that as GCD of this, it is just 7. If 7 square divides 4m plus 1, that would imply that 7 square does not divide m square plus 3. Because the GCD is just 7. And you also know that d square divides 3 times 7 to the power n. So you know that 49 divides 3 times into 7 to the power n. So we have n is greater than or equal to 2. This is also an easy observation. Now what more can we say about this? You also know that d, we have to think one thing, because d is not GCD of this thing. D is also GCD of 4m plus 1 is 49. So that is an important thing that we need to observe. We have GCD of 4m plus 1, comma 49 equal to 7. As 7 divides 49, so 7 squared doesn't divide 4m plus 1. It must hold, na? Because if 7 squared divides 49, my GCD would be 49. So 7 squared doesn't divide 4m plus 1. So highest power of 7 in 4m plus 1 is just 1. So we know that 4m plus 1 is 3 times 7. So in that case, my k must be equal to 1. K is 1. So 4m plus 1 is either 3 times 7 to the power 1 or just 7 to the power 1. 4m plus 1 equal to 7 means 4m equal to 6. So 4m equal to 6, this is inconsistent because m cannot be integer in this case, and 4m plus 1 equal to 21, that means 4m equal to 20, and that would imply m equal to 5, and you can easily check that this doesn't give any solution. You can just put the values. So what we get that d cannot be 7, because for d equal to 7 we have no solution. So let's assume that d equal to 49. So that GCD of 4m plus 1, comma m square plus 3 equal to 49. Now let's try to bound the power of highest power of 7 that divides 4m plus 1. Like we know that 7 to the power k divides 4m plus 1. I need to find k. Can 7 to the power 3 divide 4m plus 1? We know that if 7 cube divides 4m plus 1, that would imply 7 cube does not divide m square plus 3. Because the GCD is just 49, that is 7 square. Now what we can say about that? You also know that m square plus 3, it is also of the form 7, like m square plus 3, it is also of the form 3 times into 7 to the power something, say alpha, or it is just 7 to the power something. Like as 7 cube doesn't divide m square plus 3, so 2 is the maximum power that divides m square plus 3. So we can bound that m square plus 3 is either 3 into 7 square or 7 square or smaller than that. In either cases, this quantity is less than or equal to 3 into 7 square, and 3 less than 7, so this is strictly less than 7 cube. And as 7 cube divides 4m plus 1, so 7 cube is less than or equal to 4m plus 1. This implies 7 cube less than or equal to 4m plus 1. So this is less than or equal to 4m plus 1. So in this case, what do we get? That m square plus 3 is strictly less than 4m plus 1. That is m square minus 4m plus 4 less than 2, that is m minus 2 whole square less than 2. So m minus 2 whole square is either 0 or 1. So in that case, m minus 2 whole square 0 means m equal to 2, and m minus 2 whole square equal to 1 means m minus 2 equal to plus minus 1, m minus 2 equal to 1. In either cases, what do we get? M equal to 1 or 3. In either cases, you can easily see that they have no solution. You can just put the value. So if we see that 7 cube divides 4m plus 1, that doesn't give any solution. So this cannot be happen. So we have GCD is 49. So 7 square divides 4m plus 1, and 7 cube does not divide it. So highest power of 7 that divides 4m plus 1, like we call this VP. It's called a p-adic valuation. So V7 of 4m plus 1, that is highest power of 7 that divides 4m plus 1, that is just 2. So what can we say that? We already knew that 4m plus 1 is 3 times 7 to the power something or 7 to the power something. So it is 3 into 7 square or 7 square. No, can it be 3 into 7 square? 4m plus 1 equal to 3 into 7 square. Is it possible? That would imply 3 into 7 square should be congruent to 1 mod 4. Is it true? 7 is congruent to minus 1. So this is congruent to minus 1 whole square and congruent to 1. So this is 3 into 1 congruent to 3 mod 4. And 3 is not congruent to 1 mod 4. So this has no solution. So 3 into 7 square, this is not possible. So only possible solution is 4m plus 1 equal to 7 square. That is 49. So 4m plus 1 is 4m equal to 48. So m equal to 12. And you can just put the value and you can check that m equal to 12 gives me. So m equal to 12 gives me 4m plus 1 into m square plus 3 equal to 3 times some p to the power n. Now just put the value. 4 into 12 plus 1, what is this? 49 into m square. 144 plus 3, 147. That is 3 into some p to the power, and you can just factor it out easily. This is 7 square. This is 7 into 21. That is 7 square into 3. So this is not p, this is just 7. So n equal to 4. So my only possible solution is m comma n comma p. M must be 12, n must be 4, and p must be 7. So this is my only possible solution, 12 comma 4 comma 7, and we are done. As promised before, I'll give you a similar problem. Find all positive integers x, y, z in n cube such that x cube plus y cube plus z cube minus 3xyz equal to p for some prime p greater than or equal to 5. Do this on your own. You can try the factoring method to solve this. Once you have solved this out, you can type your solution in the comment box. And if you like this type of problems like solving Diophantine equations, you can keep yourself updated in this channel. Thank you.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR and IISc. For more information, visit chinta.com.